Hello, welcome back to our Qiskit computing course. In previous lesson 1, we explored quantum superposition. We use a simple quantum coin flip. Today we're taking a major step forward. So we're going to explore quantum primitives. These are the modern tools that make quantum computing programming powerful and efficient. So we'll be studying these primitives using one of the most important models in quantum physics, which is the transverse field Ising model, or TFIM, that we're going to abbreviate like that. And this model describes how a quantum spin interacts with each other and with a magnetic, external magnetic field. So it's like studying a quantum magnet at the microscopic level. This is primarily a Qiskit programming course, so I'll focus on showing you exactly how to use the estimators and the samplers of the primitives, so you can build your quantum operators or the observables or quantum physical quantities that you want to measure. In our case, which represents the state of a magnetic field in quantum mechanics, is the spin. So we're going to use SparsePauliOp operators, which represents the spin, or are useful to be the observable, the physical quantity of the spin. And this is what we're going to use to measure our complex value quantum states. So first, as previously, we have some installation requirements. Remember that you can set up your own environment. Here you have the version that we're going to use. This runtime probably is not necessary right now, but you have it here anyway. Let's take a look on our imports and explain each one. You have this block of code with the imports, and break down this a bit. The quantum circuit is our main tool for building quantum programs. You know this from lesson 1, and EstimatorV2 and SamplerV2 are two of the core quantum primitives we learned today. SparsePauliOp is how efficiently we're going to represent the quantum operators or the observables of the spin that we're going to use to build the Hamiltonian. Which remember that every time that we mention Hamiltonian, we're saying the same as the operator of the energy of the system. Is the total energy of the system. And then you're going to have the state vector here from quantum info, and this is how we're going to examine the full quantum state mathematically. And these imports, all of them are going to be from Qiskit 2.x in general, or versions after that. And we're going to build today a simulation of what's going to be a real quantum hardware. And in general, what are quantum primitives? Here I had like a quick explanation of what exactly they are. Think of them as the essential quantum verbs, the fundamental actions that you can perform with a quantum computer. So there are two core primitives. First, the sampler, which is a job that the job is to answer the question: if I measure this quantum circuit many times, what probability distribution will I get? So for any case that you have, you're going to get a probability distribution of the states, and also that amount of outcomes that you can have depends on the amount of qubits that you have. So you can have something like state 00 appears 40% of the time, state 01 appears 30% of the time, and so on, right? And the second is the estimator primitive, which answers the question, what is the expected value of this physical quantity when I measure this quantum state? So it returns single numbers. You can see it like the average of some observable. Remember that observable in quantum mechanics is the same as the physical quantity you want to mention. and measure. And the specific thing is that you represent these observables as operations on the quantum system to extract as a proper value to extract this quantity. Um, you don't need to go too much in detail of this, but the idea here is that, for example, if you are building the Hamiltonian, which is the total energy of the system, the expected value of the Hamiltonian is going to be the average of the total energy. And you can get a value like minus 2.1, or if you just check not the energy or the Hamiltonian, you check the magnetization, you're going to get the average magnetization, which can be another number like 0.8 or depending on your system, or 0.7 or any number that you have. All the time, you remember that defining this quantum system, we're going to have some uh, uh, physical magnitudes. In our case, we're going to work with everything normalized. So you're going to see values of magnetization as 1 or zero point 0.8, which is a reference value to this. And if you want to apply this to a real system, you're going to need to recover the magnitude of the, or to scale it to the particular system that you want to build. So why do these primitives matter? It's in Qiskit version 1, which is the previous one, you had to manually handle all the low-level details of the circuit execution, which is transpilation and result processing. It's transforming or coding what you are defining as your quantum circuit to a language that the compiler can understand, which is transpilation is that step. You take it to the quantum computer hardware from the classical hardware that you have and process it, and then you take the results and the result processing, of course. And with this primitive, you can focus only on what you want to compute and not how to execute it. So this abstraction works the same whether you're using a simulator or a real quantum hardware. And in our case, we're going to run everything locally, so this is going to be actually our a simulation in our classical computer, but at the end is what we will do in a real quantum hardware. So now let's see this in action by building a quantum many body systems, which is the transverse field Ising model. Check that the Ising model is defined as all the spins in a magnet. Every spin is a body, so that's why a many body physics problem. And you're going to apply external magnetic field to this material that has different bodies, which can be an array of atoms forming a crystal array. And this arrangement is going to form a metal, is any metal that you can think of. So the Hamiltonian is going to be the total energy inside this material, and then you can define it as this expression here, where you have J as the coupling strength between the neighboring spins, interaction energy, and then that means that this term is going to think on how every spin is going to interact in their next neighbor. One thing to consider is that this can be more complicated, but here we're just going to think in one dimension where the left one interacts with the right one. Notice that we're not taking 2 dimensions, right? It's not a 2-dimensional change, so we're not taking the ones on top, we're not taking the ones below or behind or anything. It's just in 1D approach. But that means that we're going to think on the spin in just one direction too, which in this case is Z. We're going to think that we have our qubit in the Z direction, or the spin being pointing up, pointing down. And we're going to see how this pointing up, for example, a spin is going to interact in the next one. This qubit can be in either state. And then you're going to have another term, which is related to the external magnetic field that you're going to apply. And this transverse magnetic field strength is going to be represented by Bx, where this is the magnetic field intensity. And this is gonna interact with the spin of of the electron that you have as a flipper. So it's going to flip the spin, and this interaction you can represent it when you have the set basis with the Pauli X operator. That's why we choose Pauli X operator in this case, because it's the same as applying the C naught gate that we observed in the previous example. So you're going to have an interaction that is going to flip up and down the spin, and also an interaction that's going to affect this alignment with the neighbors, right? And there's gonna be a competition between how the transverse field is interacting with the material, creating quantum fluctuations, and how the spins, the neighboring spins, prefer to align with themselves, because of course if one is pointing up, it's going to tend to point up with the other one. And depending on the ratio between J and B, X, you're going to have different kinds of materials, and then you can define the classical magnetic materials, paramagnetic, ferromagnetic, right? And why this is perfect for quantum computing? Well, you can define a quantum phase transition, quantum entanglement, if you can create a more complex system. This works actually quite well with materials. When you hit a quantum material, you're going to have a lot of disorder of the quantum spin, and then you can observe the evolution of this kind of systems. And usually from the quantum perspective or the quantum computational perspective, this is not a problem too complicated, but from a classical computer, you're going to struggle a lot with large quantum many-body systems. In this case, it's going to be more straightforward for this one. So it's actually a good example for testing it. So let's go to build our Hamiltonian in the code. Here we're going to show how to create, we define this method named create TFIM, the Ising model Hamiltonian. Practically here, these two fours are the sums that you saw above on the explanation, and you create the operators that you're going to apply like this, right? Where identity means that you're not going to interact with that qubit, and set is that you're going to interact with that qubit using the set Pauli matrix operator. And take into account that what you're going to have is, if you have 4 qubits, what you want to define is which qubits are you going to measure together and which ones are you going to leave untouched, right? So if you check these two, we can go above and see here that we define a number of qubits of 4. We take some Ising coupling here as 1, the transverse field Bx as 0.5. You can play with these variables, but the idea is that the Ising terms that you're going to have for the number of qubits 4 is going to give you 3 different terms. If you go check the sum, where remember that here you have I, right, which is the position of the qubit that you're going to interact with, right? So you're going to interact both here with the qubit 0 and 1 position, then with 1 and 2, and then with 2 and 3, right? Or, well, the first, the second, the third, and the fourth one. So it's what you're going to observe here, right? You have a large operator which is going to measure first and second qubit, a second large term that's going to interact with second and third, and a third term that is going to interact with the third and fourth qubit, which in these positions are 4 positions from 0 to 3, right? And the same we are going to have it with the transverse field. But if you remember, the definition that we have here is that you're going just to the magnetic field is just going to interact, or you're just going to measure the flip on 1 qubit at a time. So then you're going to get 4 positions, because you can have the first qubit, the second qubit, the third qubit, and the fourth qubit. Notice that in total we're going to have here 7 terms, and you can just, knowing now the coupling strength and the magnetic the transverse field intensity, with the number of qubits, you can estimate an energy, which you can use it like this, right? Here I have estimated of the ground state. You can define it for a paramagnetic phase where you have that magnetic field is going to be larger than the coupling strength of the spins, right? And if this coupling strength is larger, then you're going to have a ferromagnetic phase, which is going to preserve the general alignment of the spins, and it's going to be strong enough not to be affected too much by the magnetic field, right? So here, just making an estimation, you have this minus 4.33 energy estimation. Remember that you want to take these units, you need to transform the normalization of the system to general unit energies, but as general, you can use this one for scale up to any kind of system. So now we are going to understand how the EstimatorV2 primitive works. This is going to be a key feature, right? So this is your tool for measuring expectation values. Remember, this is going to be the average value of what's going to be the quantum observable, the physical quantity you want to measure. Here we have this method, which is demonstrate estimator basics. We're going to measure it on set expectation value of the state 0. In general, the expression is like this, which is the matrix operator to this vector, this transformation, and then a dot product with the same state, which means that measuring 0 on the state 0 when you apply the set matrix, right? And then you create your quantum circuit. We have this one from the previous one. You define the 0 state. You don't need in this case gates. Here the qubit is going to be an empty 1 qubit circuit, which automatically starts in the 0 state, and then you have this observable set, which is created by the SparsePauliOp operation, which is going to give you just a matrix. For these operations are 2 per 2 matrix size. And also you have this IR estimator, which creates a primitive object, and the one that's going to simulate the operation that we want. Here you can have the estimator that run the job, and then you extract the result with job.result. To have the expectation value, you just need to take the data as a float from this result and check the number itself that you returned from the job object, and then this expectation value you can expect it to be 1, because 0 is the +1 eigenstate of the set operator. So yeah, that's actually just if you check, because a spin you have 2 sides, right? You have pointing up, pointing down. So the expectation value of a state measuring 0, if you take it like pointing up, is 1, in the sense that 1 means that it's pointing up, right? It's the spin 1. If you remember that the spin actually has some dimensions, is h bar over 2. So when you recover the units of the Hamiltonian, you're going to actually not have 1, but h bar over 2, and instead of the pointing down value, which is -1, is going to be minus h bar over 2. But having a dimension is 1 and -1, the top pointing up, pointing down, right? So let's try with the state 1, which is kind of similar, right? You're going to have here your quantum circuit, you're going to have your job estimator, and the difference is that we apply here the C0 gate. Remember that this is flipping, so we flip from 0 to 1, and then you take the measurement result, and as we explained, you expect it to be -1. We can just check here everything as I mentioned it, summarizing it, and then you're going to have that here we got -1 for the state 1, we have +1 for the state 0, which are the eigenstates of the Pauli operator set. And if you want to measure something more complicated in another basis, you can get, I'll also put it on top, this plus eigenstate, which is going to be a mixture of 0 and 1. And if you measure it on the x state, you know that for plus, the eigenvalue of x is going to be 1. So that's why I use this example with the Pauli matrix operator x. Which means that, of course, when you check in the, if you want, you can print it here as a block sphere. You're going to see that instead of pointing up, pointing down, the plus state is actually like pointing in the x direction right, for example, right? So that's the main difference. But if you want to measure it on set basis, you can also do it, but you're going to get another kind of expectation values. And then everything is going to be summarized here, right? To create this superposition state, the difference with the 2 from 0 and 1 is that instead of using the regular circuit, the initializing 0, or the 1 applied with the C node, which is the X operator, we're going to use the Hadamard, which is the one that is going to create the superposition that we also saw on the lesson 1, right? That's how we can observe it here. I decide to check set, but X, sorry, but if as homework you can check set if you want to see the differences on the estimation of the values. So now creating quantum states for TFIM. To study the Ising model, we need to prepare various quantum states. So let me show you several important state preparation techniques. Here we're going to create this method, create Ising model test states. You just need to put the number of qubits. We're going to return a dictionary of the named states, and first the all up state where we define here as a QC all up, and then you just add the number of qubits that you want. So in general, you're going to have, if let's say you have 3 qubits, so the initial state is going to be 0, 0, 0. You have n qubits, you're going to have 0, 0, 0, and the number of zeros that you define in your number of qubits. And this is a simple quantum circuit. And if you want to define all of them in the down state, well, you need, here I apply a 4, where you to each qubit, to each position, you're applying the C node. When you're flipping it, you're flipping every one of them. So the mixture that you can get, something that is called like a nil state, you can create an alternating pattern. So you have QC nil, which you can think of it as a classical antiferromagnetic material, right? Which is not going to have any magnetization in particular. Magnetization order, and then this you can define it more also. Instead of antiferromagnetic, you can also have a superposition state, and the superposition state is this plus system where you have a sum of the up and down system. So the spin is not up or down, it's in a sum of these two with some probability. Here we're choosing it to be 50%. You just need to apply the Hadamard gate to every one of the qubits, which is just this 4. You check that we're calling it a superposition by applying H to every qubit here. You can just do it using as for all of these, you just need to define the metrics that you want after the as one of the methods for quantum circuit, right? And then this is a particular state, which is usually for 2 qubits, you're going to know them as Bell states, but for a larger number of qubits, like in a general quantum entangled system is a GEH set state, right? It's the maximal entangled state that you can have, and it's we're not going to go too deep on how this works, but the idea is that always that you apply a Hadamard one and that C node as a C node gate that depends on this a second qubit, you can create a superposition, and that's how you're going to get this quantum entanglement state for every qubit, and then you're going to have a more complex general state. We can also have this other initialized system like a random parameterized state using the real amplitudes and sets. So I name it like QC variational. You're going to have real amplitudes which have a number of qubits, and we're going to have this reps, which is going to be just the repetition that you want to have there. As of course, because it's random, somehow you need to define some seed. You can do it random entirely, but it's better to have a seed so you have reproducibility. So every time that you run it, you have the same values and you know that the operation is done correctly. Here we define just some kind of random uniformness by using from 0 to 2 pi this variation of the parameters, and then you have a distribution, a random distribution for of the spins. And here I add a fix because you need real amplitudes needs a circuit decomposition into basic gates, right? So that's why you need to add for this way that I'm created here for 6 random parameter state this dot decompose so you can apply it. And now we're going to just define how to visualize. Here mainly what we're doing is to visualize the states. Let's check the results. For all the states that we define on top, you're going to have a complex number, so that's why you're going to see this 0j all the time, but in general you can have numbers represented there. The first 2 are kind of boring because you are going to get 1 in both of them in the state vector, but pointing up, pointing down. And the null state, you can also get 1 because at the end you have 0, 1, 0, right? But the most interesting ones are going to be the ones with superposition, where you have a sum of different states, and then this is all plus states. The circuit depth is 1, but the number of gates applied is 3. So you have this state vector in general. You can go check how it was made, right? It's all the plus states. And you're going to have in total 8, 3, 6, 8 states representing all the combinations, right? It's 2 to the power of 3, right? And because we made a superposition state, we're going to have the same probabilities, and that's why we have the same number for all of them, right? And you can also check that for the other states and check the calculations. Remember that the GEH set state is the most entangled system, but it was equally distributed, so we have probabilities of 50% to get in 0, 0, 0 or 1, 1, 1, 1. But the variational state that we create on top is going to have random probabilities, and that's why you're going to have a randomness of probability distribution. But if you take the norm, this is already the probability. So if you sum these values, you need to always get 1 because the total probability needs to be 1. So now let's use the EstimatorV2 to measure the physical observables in our TFIM system. This is going to demonstrate the real power of quantum primitives for scientific computing. We define the measure TFIM observables. Here we need as inputs states, the Hamiltonians, and the number of qubits. Here I have a quick explanation on what's this. The idea is that we're going to create our estimator and a dictionary to store different observables. So first we need the Of course, we define the estimator as the error estimator, and we have these observables defined as a list, name observables, where we are going to store the Hamiltonian expected values. Check that we define energy as Hamiltonian, and Hamiltonian is already defined on top, right? This is straightforward because we directly measure the Ising model Hamiltonian that we built earlier. And then next we have the set magnetization, which is defined in this four. We add all the terms that we create using the Pauli matrices, defining which qubits we're going to have. So you have the sum of set 0, set 1, set 2, and set 3, which measures the total spin in the set direction. And similarly to this, we have X magnetization, which is going to be the next one. Remember that we have the total amount of terms that was 4 when we choose 4 qubits. So it's going to be proportional to the number of qubits. And then you are going just to have the interaction of, or the flipping of every qubit in all the positions, right? This is quite similar to what we already have built also earlier. And then you can check the definition here of these correlations, which you measure the terms set 0, set 1, plus set 1, set 2, plus set 2, set 3. And this is the correlation of the nearest neighbors. And now that's going to have a measurement loop. So you have for state, to measure all the observables for all states, you're going to have a state name and circuit, and you're going to pass this in for all the states here, right? And that's why you define it like this. Remember that you have these two, and you're going to pass all the states using the states.items, and you're going to need to check this as or to understand this as the nested loop measures, which every observable is for every state. So the EstimatorV2 pattern is always the same. You're going to run, you're going to get result, and then extract the expectation value, which here I'm just printing everything like that. And which is beauty of this way to doing it is that each measurement gives us the deep insight into the quantum many-body system of our system, right? So let's check the results. We're going to have here for the different system. This looks quite well. You can see that how different quantum states have completely different physical properties, and the all up states has maximum set magnetization here, which is 3, and the GAH set state, which is here around, you can expect it to have quantum correlations as 2, which makes a lot of sense if you think it when you're measuring this expectation value, because it's the one that is with the maximum entanglement. So of course it's the most correlated state possible here, and you can observe stuff like this for all of them. For example, for the X magnetization on top, you're going to have the high magnetization state, which is this one, right? The all plus states here, right? Magnetization on X. Remember that at the end, the plus state, or when you apply the Hadamard to the 0 state, you have a superposition of 0 and 1, which at the end is a way to describe the qubit. Instead of pointing up, pointing down, is pointing to the right or pointing to the left. So of course, when you measure magnetization on X direction, you're going to have the maximum direction. One detail is that you can define with other matrices and other different states also Y direction if you wanted to. In this case, because X is the simplest case, if you check the matrices, X is all real values in the matrix, so it's the one that we usually use, but perfectly you can just define Y and do everything with the not the plus state but other state that is specifically the proper values of Y magnetization. So going down, we need to check this as these results. We here I create just a visualization dashboard. This is mainly this block of code is not Qiskit related. Is mainly just functions to plot it. So you can observe here that at the end you can check details, but you're going to have the magnetization components, the energy landscapes, the observable heat maps, and the details summarized in tables. So you can check here depending on your results, and if you want, you can play with the constants of the coupling strength and the magnetization, the transverse magnetic field constants, and see how these values are varying. So advanced primitives, the parameter sweeps and optimization. This is probably the most powerful feature of EstimatorV2. This let us study how quantum systems change as we vary parameters. Here we're going to mainly, instead of applying the Pauli matrices, we're going to define our quantum circuit with n qubits, which in this case we define as 4. And we're going to define a theta parameter as this, as parameter, we name it theta, and it's going to be used as the rotation angle on the rotation matrix in the y direction, with this is this ry, and then we apply a rotation angle theta in the y direction to the qubit number I, right? Here I'm just printing this information that you can see below, and then you need to create some observables as previously. So it's again repeating the same steps of the magnetization on Z and the magnetization on X, remembering that you need to have the Pauli string terms depending on how you're going to measure this. But the important part is goes here to the parameter sweep. So the theta values are going to be this line space vector. You define a no and p that line space that is going to have 21 positions from 0 to pi, equally distributed, and then you're going to run theta from these values, and we can observe how it works. You define the create estimator, you prepare these angles in an array of the parameter set, and this is how each parameter values is wrapped in a list, because circuits might have multiple parameters. So now the magic goes in the energy, job, and estimators, and set estimator and X estimator. This is going to run efficiently the measurements of all the magnitudes or observables that we want to measure using these vectorized inputs, right? This is defined as the estimator.rom. You put the quantum circuit that we just have defined and the operator that you want to create. Notice that we have Hamiltonian from the Hamiltonian that we built on top with the particular constant that we define. We here just define Z magnetization and X magnetization as these ones here, and well, the parameter sets, which comes from the array of theta angles that we're going to use on the Y rotation operator. And then you can just get results. We store the results in energy results, at magnitude results, X magnetization results, using the job function with the method result on top, and taking the first value 0, right? Here is we're going to have the classical expected value, the classical value store from the expected value that we measure. And then you can just this is a vectorized execution, so instead of 21 separate functions calls, EstimatorV2 processes all the parameters values in a single batch, and the result is arrays of expectation values, not single numbers. So this is incredible efficient and show how Estimator V2 is designed for a quantum modern algorithm. In our case, in our computer, is not be optimized in that way, but is when you transpile that to the quantum hardware, it's going to work better optimized, and this optimization is crucial, so it works efficiently, and we can run this, and easily you can observe here all the parameters that we estimate. The total measurements and total of the parameterization suite was 63, and you here can show energy and magnetization and how it changes smoothly. The execution time efficient vectorized processing here, and let's check here the transition phases, right? So check here how, depending on the phase or the theta angle, that remember that we vary from 0 to pi. That's why you have here like 1, because we normalize the angle respect to pi. But you're going to observe how the energy varies and how it's maximized at certain point, at certain phase. You can then only check the magnetization for X or Z and see how it evolves, also to check that the maximum magnetization at X is also where you have the maximum energy. And you can check also their values like the phase of the magnetization defined here, and you will also put here like the energy derivative, which is the critical point, observing where we have a 0 in the derivative and the optimized part, right, which we see here that is at 0.5. Also what we can observe easily here from the first plot, that we have the maximum and -2 when you have 0.5, right? So of course you're going to have the 0 also here, but also you see you have zeros in these points, but these are minimum points. If you observe also the plot, I think it's easily correlated between these two. Here you have some of the estimated value of the phase transition analysis, and this is a way to observe how the system evolves depending on the rotation that you have. Imagine that then that the spins are not well organized, because you cannot really know if the spins are going to a specific direction, but you know that in general they're going to be normalized, and they're going to have this behavior or energy when you apply the magnetic field in a specific direction. So then we're going to understand the sampler V2 primitive. This sampler is going to get the probability distributions. In contrast to the Estimator V2, here we're going to make a demonstration. Again, we're going to define the sampler as this method named RSampler. Here we're going to have 3 qubits. So we define the state for this case, example 1, 0, 0, 1. And the number of qubits that we have here is, then we're going to apply to the qubit number 2, which is the third position. Sorry, in the vector, you remember that we have position 0, 1, and 2. The X operator, which is going to flip it. So we pass it from 0 to 1, and that's how we get this state. And then we are going to add the measurements, measuring all of them. We're going to get 1,000 shots, and then get the result from this job, and then have a measurement of the counts of the result, right? Here we're going to print the values and a dictionary of the counts, so we can actually see the number. And also, if you want to check another states, I'm going to leave these ones as examples for a superposition state, like that. To go faster, I want to mainly check here at the end. So you see that you can prepare different states, and in this case we prepare state 001 for GHC 000 plus 111 maximum entanglement, and between this You all can check the sampler versus estimator comparison, which the key difference are that from estimator V2 we need classical bits and explicit measurements, and we need specific shots, the number of measurement repetitions, but the result is a probability distribution of the expectation values. We have here then expected 50% and 50%, and also remember that the sampling, you're getting just how many times you get one state or the other, and not a particular physical quantity. Um, from the previous one, we got stuff like variables like quantity, sorry, as magnetization, energy, uh, magnetization in X, magnetization in Z, or the energy of the system, or the energy of just the magnetic field. And this is then the estimator is going to give you numbers like the average quantity of some particular measurement, but sampler V2 is going to give you a statistics like state 00 appear 50% of the times, right? Both primitives are essential, so you use estimator V2 for optimization and energy calculations, and sampler V2 for the sampling and probability analysis, so you know that also the state is behaving as you want to. And this here, example 3, you can check it to check the statistical noise. I'm going to go here to the next one. Okay, so understanding the sampler V2, as I mentioned it with the estimator V2, the difference that you get average values from physical quantities, but sampler is, as its name saying itself, is that you're going to have like a statistic analysis from the system. So here is easy. You can define again the circuit that you want to. Here, let's check just this state. This first example, you can check all of them afterwards. For this first one, you just define a quantum circuit with a specific number of qubits, and in this case it's 3 qubits, and in the third qubit, which is position 2, we're going to flip the last qubit, and that's why we have 001. And then for this particular one, you're going to add measure all. This one, again, you can just do the sampler run of this. This is going to be this job. You get the result, and the result you can get the counts. In the sampler, you get counts because you're going to have the a statistical distribution. And going here to check this result, if you see from the sampling product from 001 and 1000 shots, you get the state 100 1000 times, right? Because of course it's the only state that you have, so you're going to have this state 001 100% of the times. For more complex states, like for example super entanglement state, GHZ state, you can have a superposition where you have 000 and 111 over square root of 2, which means that you have 50% both of them, and as you can expect, if you run it 1000 shots, you're going to have some distribution that goes close to 50%, which in this case is for 000 and 111. You see that you almost have here almost the same amount, almost 500. So you have closely 50%, which if you increase the number of shots, you're going to have a value closer to 50%. And the main difference with the sampling is this, that you're going to have statistical distribution, and with the estimator, you're going to estimate a magnitude, a quantity, a physical quantity, which is the expectation value of that. Okay, so I don't want to make this video too long. So here I'm gonna leave you an example on how to build a complete analysis workflow, and then the idea is that you can check this one if you want to, and then if you have time, and then you can visualize these results. In general, here what you're going to define is a more complicated a general Hamiltonian. You can play with it. You're going to have the complete workflow of what we have just done, and observe the samplers and the estimators. And also you can check that even you can see the randomness, or let's say more like the amount of states that you have, which is going to be estimated as the quantum entropy. And the evolution of this one depending on the variables. Here I play with some of the values, so you can play with the magnitude of the transverse field and get different ground state energy, different order parameters for both Z and X magnetization. This is normalized with the number of qubits. The quantum entropy, you can see also how it evolves with the different magnetic fields, and you can also classify it on the quantum phases, right? Depending on, you can see how it evolves the order parameters when you have different transverse field with a specific. Here I left J as a 1, so you have a threshold at 1, and on how when you change phases. Of course, when you are in this red zone, is going to be the classical zone, and when you're in this blue zone is the quantum phase zone, where you have large magnetic fields. This is because the fluctuations due to the magnetic field in the material are going to be large enough, so you're going to have you're going to be overpassing or surpassing the coupling strength between the spins. So you're overcoming the strength, the internal strength that have the magnetic field of the material, the intrinsic magnetic field, with this perturbation that is the transverse field, right? And here I leave you as in the previous lesson some key takeaways and physics insights. You can check them in the description. Here I don't think it's too necessary, it's details or summaries of what we just observed, mentioning what we concepts as the many body systems, the observable measurements, and practical applications, experimental connections. But mainly as a conclusion, you have just accomplished to see an example of the quantum primitives, to explore quantum many-body physics problem, implemented also a general advanced workflow with a parameter suite optimization and analysis. You have connected a theoretical concept and model with a practice exercise, and you develop some visualization skills if you take all these plots and dashboards that I presented here. And as a bigger picture, we're going to keep going for more foundational that are going to give us more quantum algorithms in the future. And then for future stuff, for future algorithms, we're going to get variational quantum eigensolvers. You're going to mention also these quantum approximate optimization algorithms. We're not going to go too deep on that, but this is also applied to quantum machine learning, quantum chemistry, which are systems like this with some particles or quantum particles interacting between them, and some quantum error correction, which is going to be the how noises add to our system. Okay, so thank you for this, and I will see you in the next one.